Hello everyone, welcome to my presentation on our paper Re-examining Distillation for Continual Object Detection. I'm Eli Verwimp and this is work I've done with Kuo Yang, Sarah Pariso, Hong Langcheng, Stephen McDonough, Eduardo Perez Pelitero, Matthias de Lange and Tinne Duitelaars, working either at the KU Leuven or Huawei's NOAS ARC Lab. Before we begin, a brief introduction on continual learning in object detection. In continual learning, the goal is to learn a sequence of tasks without being able to access the previous task. And the goal is to learn all tasks well. So when you're training on a new task, you don't want to forget what you've learned during the previous tasks. A typical benchmark in continual object detection is VOC 10+10. What you do there is you divide the VOC benchmark dataset into two sets of 10 classes, and then you see only the images and the annotations that have annotations for those classes. For instance, at T1, which we use to indicate the first task, horses is among the 10 categories that is included in this task. So you see images that have annotations for horse and other objects, of course. In the second task, there's the person class, so you see images that have person annotations. Now, something that can't happen in continual object classification is that you see the same image during different tasks. For instance, in the image with the horse and the person on the bottom, you will see this image in the first task with an annotation as a horse, and in the second task with the annotation for the person. We'll see later during the presentation that this is actually the source of one of the major issues in the distillation of continual object detection models. So one of the most popular methods in continual object detection nowadays is FASTER-ILOT. FASTER-ILOT works by using the FASTER-RCNN backbone or FASTER-RCNN model and applying distillation on all three levels of the FASTER-RCNN architecture. So you use distillation on the backbone, on the RPN, on the region of interest heads, and then you use the student to learn the new annotations. The teacher, of course, has been trained on the previous task so that it has knowledge of the previous task, and it can distill this knowledge into the student. Now we found, and we will elaborate this a bit more later during the presentation, that the distillation on the backbone and the region proposal network work pretty well. It's in the region of interest heads that the distillation is too strict and prevents the ryots from the student from learning the new annotations. So we've actually got two goals. One, we want to retain the knowledge from the old tasks that is present in the teacher model, and we do this by using knowledge distillation at three levels in the FASTER-RCNN architecture. Our second goal is to learn new tasks from the newly annotated data as well as possible, without forgetting the previous tasks. If we train, for instance, the VOC 10+10 second task, we see that actually not all classes are learned equally well. In particular, three classes are at only 60% of the performance of a model that would be trained jointly on all 20 classes of VOC. This is the table, the plant, and the TV. So we ask ourselves, why is this the case? Why are it these classes that are learned much worse than the other classes? So first we looked at the RPN. And the RPN, you can see if you use FASTER-ILOT, the method that I explained in the beginning, where you use distillation at all three stages, actually detects almost all ground truths after you've trained on a second task. Even if you fine-tune, so you don't use any continual learning method, you still find almost all of the objects after training on a second task, even though there's no method to remember the objects of the first task. So the problem is not in the RPN, but it is in the region of interest sets. In these graphs, we see a percentage of objects of either T1 or T2 that are classified correctly, wrongly, or as background. In particularly, we see for the second task objects, when you use the distillation method, that 76% of the objects are classified correctly, but 18% is classified as a wrong class and 6% as the background. So the problem is mostly in the not learning to classify the new classes, because in the objects of the first task, you still get above 90% of classification accuracy in the model. So we tried to look at how we could reduce this 80% error and the 6% background error, and how we could let the model learn the new task better. And we identified actually two problems, and it both stem from the appearance of objects of later tasks in former tasks but unannotated. In case of the image with the horse and the person, the model doesn't know during the first or the former tasks whether this person belongs to the horse or whether it's just part of the background, so it learns to classify it either as part of the horse or as the background. But when you then see in the new task an annotation for this person, you still are going to distill the knowledge on the teacher in the student model. But since the teacher model has learned to classify that a person is usually part of a horse or it's the background, the scores for horse and background are going to be high. This is a conflicting signal because on the one hand you want to keep the classification score for the horses and the background high because that's what the teacher tells you to do, but on the other hand you want to match the annotations for the image, so you want to classify this object as a person. And this is a conflicting signal that your model has to overcome, which doesn't happen by default if you use the distillation losses as I've introduced them before. And if you look at how high these scores are from the teacher model, the wrong scores, we see that they highly correlate with how often they were present in other images from the former task. Here we see the example of how often these objects occur in images with chairs, which is also an object that is in the first task. We see in particular that the TV, the plant, and the table, which are the categories that weren't properly learned, occur more frequent with chairs and thus have a higher background score or a higher score for a different class or the wrong class. The person is the outlier here, but since there's so many persons in the second task, it's about 50% of the second task, the model is still able to overcome the wrong classifications and the wrong predictions of the teacher model. We solve this by using two techniques. When the overlap with the new annotation of so if the teacher outputs a region and it overlaps highly with a new annotation, we know that this output of the teacher is actually wrong. So we can just discard it and filter those outputs of the teacher and not distill them. This is a very easy approach and it is already effective. But there's still objects that overlap, or outputs of the teacher that overlap a bit, but with an IU then less 0.5, that have a high score for either the background or or a wrong category, but still contain a significant proportion of the new object. And this is where the MZ loss is a problem. The mean squared error is quadratic, and if these scores, as we've seen for the teacher, are higher than usual, or are very high, then the MZ loss will very quickly dominate all the other losses. So if we change instead to a Huber loss, we maintain the same loss values for the lower values, so for small changes in the student network compared to the teacher. But if these changes are becoming so large that the student is pushing towards a different classification, then we say like, okay, we're not going to punish this so hard such that the student can actually learn new things. And we assume that if the student is willing to push over this large loss difference, then it's actually trying to learn something new. And if you look at our results and we compare this to Foster-Eilert, the original method, we see that we actually do better on all tested benchmarks. For instance, on the VOC 10 plus 10, we lose a little bit of accuracy on the first task, but the second task is learned significantly better. On the other tasks, 15 plus 5, we do better on both tasks, and also on 19 plus 1, we do also better on both tasks. On Microsoft Cocoa, we don't have results for each task here, but we see that ours on average for the 40 plus 40 benchmarks does about 5 MAP points better than Foster-Eilert. So in conclusion, most continual learning issues in continual object detection are in the region of interest heads and not in the RPN. The careful application of distillation can improve the effectiveness, and there is a lot of room for improvement by leveraging rehearsal techniques, which you can see in the paper. I want to thank you for your attention and hopefully see you at BAVC. Goodbye.